Section 10.7, parametric equations. We're just going to look at a little bit of this section. Just want to at least give you a little bit of exposure to parametric equations, what those are all about. If you're heading into Calc 2, again, I'll tell you a lot of this stuff, calculus, Calc 2 especially, we'll deal with parametric equations in a lot more detail and get into those. But at least want to show you what parametric equations are, how we graph these things, talk about some of the terminology associated with parametric equations. I'm going to leave off the application stuff, just to make it a little bit less stressful for us. But at least let's just cover the basics of what parametric equations are. Now, the idea essentially behind parametric equations, you're plotting points or graphing an equation in the xy plane. We have our ordered pair as xy. And, typically you have an equation, you plug values for x, you get your value for y, you plot your ordered pairs, or you play connect the dots, or even if you graph it on the calculator, you're just looking at those ordered pairs. What parametric equations allow us to do is bring in a third variable to where we can represent our ordered pairs x and y in terms of another variable. We call it the parameter. Oftentimes t is used, not exclusively. I'll show you an example with something else, but primarily it's t because often t, or that parameter, is time. So that not only can we plot the location of an object in space, but we can also plot its location with respect to time. So a lot of times you'll see this used in physics, especially to trace out particle motion or motion of an object over time. So I have not only its location, but when was it located there, that kind of thing. All right. So the idea then again is I'm going to represent our curve using two equations instead of one. So using f and g, if those are both continuous functions. Now continuous, that's our fancy word that simply means you should be able to draw the graph by putting your pencil to paper and not picking your pencil up until you're done. That's essentially what continuous means. But that's a good calculus term. When you get to calculus, we talk a lot about continuous functions and continuity of functions. But if f and g are continuous functions of t on an interval I, so we're putting limitations on the t values, then the set of ordered pairs xy, such that x equals f of t and y equals g of t, is a plane curve. That simply means it's a curve graphed in our flat two-dimensional coordinate plane. The equations x equal f of t and y equal g of t are what we're calling these parametric equations for the curve, and the variable t is a parameter. So again, x and y, to get your ordered pairs, you have separate functions to do that. Right? And so for example, graphing the curve represented by the equations, x equals 1/2 t, y equals t squared minus 3, putting limitations on t from -3 to 3. Now, you don't necessarily have to have limitations on your parameter. We do in this case. So when I'm coming up with my ordered pairs to graph or plot in our plane, those are the only ordered pairs that we're interested in, or in other words, over that interval with respect to t. So in other words, I don't care what happens outside of the interval from t equals -3 to 3 with respect to the graph of our curve. So you do have to be aware of that. If I do have limitations on the parameter, I'm only graphing a part of the curve. So all it is after that is really just plugging in values. I mean, that's all this is. So I have my t values from -3 to 3, so we always recommend plugging in as many values as you can to get a good picture of the graph. And then we're plugging in those values into each of those two equations to get the x and y coordinates. And so I end up with those ordered pairs for x and y. We plot those points, and we have the graph of our curve. Now notice again, since t was equal to -3, that was kind of call it our left bound or minimal values for t, then the first point that gets plotted is that point -3 6. And then when I hit 3 for my t value, I've got the point 3 + 6. That's the last point on our curve. So there are no arrows like we would normally draw on a graph like that. We're not drawing those here because those are stopping points for this curve. Now, what you will see done, look at that weird looking thing. Try this one more time. What you will see done is arrows placed on the graph to represent the direction of the object, however. All right, now this textbook, this doesn't address that, but again, if you're heading into the calculus, we will definitely talk about that. So in other words, not only do I want to show that this point or this graph is starting at the point -3 halves 6, but as you move through your t values from smaller to larger t values, I'm tracing out the path of my object or of my particle. Now again, I still don't want to do that and put that arrow on the endpoint, because like we said, the graph stops at that point, and that can be misleading to think that, well, like we normally would say, the graph continues, and it doesn't. So I don't put an arrow on the endpoint if my graph stops. All right, but you will see the arrows placed along the curve periodically, just to show the direction of the curve. Now again, this textbook doesn't do it, so I'm not going to talk about or worry about direction. Okay, but that is the more general or the broader application of parametric equations. Right, but that's it. I mean, that's the idea, at least in terms of graphing. Right. Now the other part of this is going to involve what we call eliminating the parameter. We're still graphing the same curve in the same coordinate plane, using the same ordered pairs x and y that you would use if you had this written as a two-variable equation, instead of bringing in this third parameter, or this parameter t. So we could also then represent this curve using a single equation in terms of x and y. Right? We call it the Cartesian equation, or the rectangular equation, like what we talked about before when we were doing, polar and rectangular graphs or points. Right? So a rectangular curve, or a Cartesian equation of your curve, as opposed to a parametric equation for your curve. Now, looking at the graph of this thing, I mean, it looks like a parabola. Right? So we should be able to come up with maybe something that's quadratic in form to represent that graph. Now, you can do this a couple of different ways. You have two equations here. You have x equals 1/2 t. You have y equals our other equation, t squared minus 3. The idea is to eliminate the parameter, meaning I want to write a single equation that contains only x and y. Now, you can do that two different ways. And really, this is based upon, if you remember in algebra when you solve like systems of equations, one of the ways that you can do that is to solve one of your equations for one of the variables, and then you sub out that variable in your other equation. That's one way that we could solve, or not solve, but rewrite these two equations in terms of one. So in other words, if I take the equation x equals 1/2 t and solve it for t, so that t would be equal to 2x, and then I can sub out t in my y equation. Since y was equal to t squared minus 3, I'm just subbing out t with 2x. And I get the equation y equals 2x squared minus 3, or 4x squared minus 3. So that is an equivalent equation, at least in terms of the graph that you're seeing here. Now, what happens when you do it this way, when you eliminate the parameter, you lose that direction component thing that I mentioned back here, right? Because no longer you're plugging in the t values, or like we said, typically time, to indicate when your point is at a particular location, right? You're just graphing, but the graph is going to be exactly the same. It's still a parabola, right? I mean, that's 4x squared minus 3. But it's not the entire parabola. Because of those limitations on t, we also have to limit what part of the parabola we're looking at, right? Because we're not looking at the entire graph. So what you also then have to do, if you eliminate the parameter, you also then have to adjust the limitations on your variable. And depending upon which way you write it, it's typically most common that you would represent or put the limitations on your input variable. All right, so since we wrote the equation in the form of y equals 4x squared minus 3, x is our input variable, our independent variable. So we're going to put the limitations on x. You could just as easily take in the equation with y, and you could solve that equation for t, and then sub out the t in your x equation. All right, that would be a little bit more Not much more difficult. They're a little bit funkier looking, but it could be done. I'll do an example. My next example, I'll show you both ways. But it's really, you could do it either way. The idea is I want one equation involving x and y. Which variable you sub out, yeah, we tend to want to put it in y equals form, but it doesn't necessarily have to be. But in this case, since that's what we did, we subbed out the t in the y equation. I have x now as my input variable. So I want to express my equation, y equals 4x squared minus 3, but only with respect to values for x. And again, really you got those, you have those in your table anyway, because that's what we did up here to get those points. When t was -3, x was -3 halves. When t was 3, x was 3 halves. So instead of going from -3 to 3 on my t, I'm going from -3 halves to 3 halves on the x. But you have to include that because of the limitations on the parameter. Even though we eliminated the parameter, we're still not looking at the entire graph of this function. We're only looking at this part of it between -3 halves and 3 halves. So that is part of the deal with these parametrics when you eliminate the parameter. Next one, to give you another example with it. Graphing the curve represented by the equation. I'm going to show you how to do this one on the calculator as well. Then find the equivalent rectangular equation. That's a rectangular equation or Cartesian equation where you eliminate the parameters. So here we have x equals t cubed. We have y equals square root of t with limitations on t between 0 and 81. Now in this one I'm going to do both ways in terms of limiting the parameters. So we're going to find our restrictions on x and y depending on which way we do that. And this one I have worked out for us. So I have x equals t cubed, y equals square root of t. Now I went ahead and made a little table of values. Now I'm going to be a little bit careful here in terms of the values that we plug in because of the calculations that we have to do. Remember, y is the square root of t. So I mean, I could plug in anything between 0 and 81. What I chose to do was plug in a few perfect squares so that when you did the square root of t, you got nice numbers. But you could, you could plug in 5 if you want to, and you get the square root of 5 and doing a decimal approximation there. But I just plugged in a few values that gave us, nice numbers for our coordinates. But again, there's no other limitation otherwise. So I just made a table of values. I plugged in values for t. I did 0, 1, 4, 9. I skipped a couple. I did 25, 81, just to give us a few points on our graph. And then I got my x values, which were t cubed. So my x values get pretty large pretty quick. All right. Cubing 1, cubing 4, cube 9, cube 25, cube 81, which is our endpoint of our graph. The y values are not so bad. I mean, that's just square root of 0, 1, 4, 9, 25, 81. So those are not bad numbers. That's why we chose them. Now, plotting those points on a graph is what it is. They're just big numbers, at least with respect to the x's. Now, on your calculator, if you want to graph a parametric curve, or a curve defined by parametric equations, you go to your mode setting, and this is the same place we went when we did our polar curves. Go to your mode setting and you're going to change that to parametric. And then you go to your window settings. Your window settings are now going to have Tmin and Tmax because, we have our third parameter t, or our third variable, our parameter t. Now remember, like I said, remember that button I said has the x, the t, and the theta and all that on it? So it just depends on what mode you're in. And when you're in parametric mode, when you hit that X button to put in your variable, it's automatically going to put in t. Now on your Windows setting, you have a Tmin, Tmax. So in this case, Tmin is 0, Tmax is 81. T-step, same thing we talked about with the polar graphs. The T-step, that's how fast it's going to draw the graph. We're a lot more interested in that here with these parametrics because like I tell you, we do want to know the direction of the curve. I went ahead and set this one to 1 just because those numbers along the x get very big very quick. All right, and so I wanted to draw the graph. If you set it to 0.1 like we did for the polars, it'll draw the graph. It'll just draw it really, really slow, and so it takes a little bit longer to draw it. And that's the one thing you do have to be careful of with these, both the polar curves and the parametrics. If you set your t-step too small, it may take a while for the calculator to run through all those values and draw the graphs. Right? But But this one still is not too bad, even if you leave it at 0.1. But I went ahead and did mine to 1 to do the graph pretty quickly. But you can also see the path that the graph is tracing, right? The path that the graph is following. And so when you're talking about motion of an object or particle motion, it gives you more of a visual of exactly what that object is doing. That's the idea. The X-min, X-max, of course, since our X values got pretty large, I went ahead and set my X-max to 600,000, which was beyond our largest X value. And I just went ahead and set my Y-max to 10. And that way I get a nice picture of the graph, the basic shape of it. Now, because there are limitations on your parameter, on T, then when you set that T-min and T-max, that's the first point and last point that it's going to plot. All right, so it'll start the graph where you tell it to start. It'll stop the graph where you tell it to stop. Now, to enter in the equation, you hit your y equals. And when you hit your y equals button, now, as happens with each different mode setting, you should now have an x and y. So you'll have an x1 equals y1 equals, x2 equals y2 equals, x3 equals y3 equals, right? So you'll have sets of parametric equations that you can graph. So when we do function mode, our basic mode, right, we have y equals. When we do polars, it was r equals. And now when you do parametric, it gives you x equals and y equals, so that you enter in your equation. And then again, when you hit your button for the x, for the variable, it's automatically going to put t into your equation. So with all those settings, and then you can hit your graph button, and the graph that I have up here is basically what the graph is going to be that you are going to look like that you get. Now notice again, the graph will stop when it hits that point, 531,441.9. All right. And it won't go beyond that point. Now, like I said, these are not as interesting as the polars, but they're a little more interesting than just basic y equals functions or y equals graphs. Now, eliminating the parameter. Again, like we said, you could do that with either equation. So I went ahead and did it both ways this time just to show you how that could be done. So let's say first I want to eliminate the x. As we did in the previous example. So I would take that equation, x equals t cubed, and I'm going down here and I'm just solving it for t. And if you solve that for t, you get t equals cube root of x. And then I plug that into our equation, y equals square root of t, to get y equals the square root of the cube root of x. And then I just rewrote it from there. So that would be x to the 1/3 raised to the 1/2, which would give you x to the 1/6, or the 6th root of x. So y equals the 6th root of x. Now, since x is now my input variable, I want to represent the limitations on x. And you can get that again from your table, or at least plugging in the initial value for t and the terminal value for t, which was 81. So x goes from 0 to 531,441. And that's my limitations on x. But that has to be included. If you have limitations on t, you must have limitations on your input variable when you eliminate the parameter. Conversely, or the opposite direction, I could eliminate the y if I chose. It's all about representing or putting the function or the equation in terms of x and y and eliminating the t. So in this case, if I took y equals square root of t and we solve that for t, we get t equals y squared. And so then I'll plug that into our x equation. So instead of x equals t cubed, I've got x equals y squared cubed, plugging in y squared in place of t, or then x equals y to the 6th. Perfectly good equation to represent the graph that we have above. Now this time though, y is my independent or my input variable. So I put my limitations in terms of y. And y went from 0 to 9. We had that in our table. And again, that's plugging in t equals 0 and t equals 81 into our y equals equation. Right. So yeah, like I said, these tend to not be too bad. I mean, the numbers here are not that great because of the large values along the x-axis, but hey, that's real world type stuff. Numbers aren't always nice little small integers all the time, right? But yeah, so either way you care to do it, it could be done either way when you eliminate the parameter. This one's another example because it also ties us back a little bit to the trig. A little bit different in how we're going to eliminate the parameter. So, and even not eliminate the parameter, but finding the Cartesian or rectangular equation to begin with. So to find our rectangular equation, we have x equals 3 cosine t, y equals 3 sine t. We do have the limitation that t is between 0 and 2 pi. This one we're relying more upon, instead of, like we did with the previous, just plotting a bunch of points. I took a shortcut with this. I mean, you could still plot points if you wish. You could plug in values for t between 0 and 2 pi. Do a bunch of sine and cosine values. If you did something like that, you would want to pick those nice t values, like pi over 6, pi over 4, pi over 3, pi over 2, things like that, to give yourself nice values, or at least ones we're familiar with. But just to point this one out, and I maybe want to hint, pay a particular attention to this one. Using the fact from our identities, I was searching for my word there, our identities, our Pythagorean identities, we know that sine squared plus cosine squared equals 1. So if I take each of x and y, 3 cosine t and 3 sine t, and I solve each of those for sine and cosine. So for x equals 3 cosine t, I could say that cosine t equals x over 3. For y equals 3 sine t, I could then say that sine t equals y over 3. And since cosine squared plus sine squared equals 1, that's a Pythagorean identity, I'm just replacing cosine and sine. Cosine I replace with x over 3, sine I replace with y over 3. And I have x over 3 squared plus y over 3 squared equals 1. Or x squared over 9 plus y squared over 9 equals 1. And then clearing the fraction, multiplying everything by 9, I've got x squared plus y squared equals 9. And that you should recognize as the equation of a circle whose center is at the origin and it has a radius of 3. Okay. Now we did go for t between 0 and 2 pi. All right, so that'll take us one complete rotation or revolution around the circle. Right? So what you would oftentimes see in a case like this, that's what I mentioned earlier, t is oftentimes used as the parameter. You may see theta used in this case, right? Since we're using these trig functions, and I could let theta be my parameter, right? The angle of rotation, instead of t just being time, right? So yeah, so it could be different depending upon the context in which it's being used, but it's still arbitrary. I mean, you use whatever variable you want to use. It's just that t and theta are the most common when you're dealing with these parametrics. Now, we get that equation of a circle whose radius is 3, and you could put your limitations on your variables based upon that fact. The fact that it is a circle with radius of 3, so I know that x and y have to fall between -3 and 3, right? The center of that circle is at the origin, and then given just the basic shape of that graph, circle with radius 3, we know that x and y values would be go from -3 to 3. So that would be our limitations on our variables. Lastly, in this section, finding two sets of parametric equations to represent a Cartesian equation. Right? So with the previous, we were taking the parametrics and we were finding a Cartesian equation or rectangular equation to represent the parametric equations. Here we're going in the opposite direction, and we're representing our Cartesian or rectangular equation with parametrics. And that's actually, it's a little bit easier than it sounds. One way that you can do it, so in this case I'm starting with the equation y equals 4 minus x plus 3 squared. One way that you can do it, and I call this the cheap way, if you simply replace x with t. If x equals t, then y would equal 4 minus t plus 3 squared. All right? So we call it, that's like I said, that's the cheap way. That's the shortest way to do it. Just simply let x equals t. There's your first parametric equation. Let me switch this out. I don't like that. And then if x equals t, then in our equation, y equals 4 minus t plus 3 squared. And then I just multiplied all that out to get this equation. Okay. But yeah, it's that straightforward. Now, to get a second one, now really, you can do any substitution that you want. It's all about, I always say, start with x or whatever your independent or input variable is here. And you can really just replace x with anything you want in terms of t. Right? So again, the simplest way is just to let x be t, and then there's your second equation. But I can let x be anything. I can let x be t plus 2 if I wanted to, or t minus 5, or t squared, or anything you want to plug in there, as long as it's in terms of t. Because that'll give you your first equation, x equals whatever you just said, and then you plug that into your y equals to get your second equation. So in this case, we said let's let x be t minus 3. And the reason we chose t minus 3, because notice if you plug t minus 3 into your equation in place of x, I've got t minus 3 plus 3, which simplifies to just t, and I get y equals 4 minus t squared as my second equation, right? But really, it turns out that there's an infinite number of ways that you can do this, right? And when you have parametric equations, or you have a rectangular equation that you want to represent using parametric equations, there's an infinite number of ways that you can choose to do that. So I always say that the easiest way, let x be t, there's your x equation, and then we plug that into our y to get our second equation. But then there are other ways that you can do it. Right? So in your homework, you're going to see these types of questions where you're asked to represent your Cartesian or rectangular equation using two sets of parametric equations. That's how you do it. But ultimately, like I said, there's an infinite number of ways you can do it. So there's no limitation as far as what those equations can look like. All right. Now that's as far as I'm going to go with this section. If you notice in the notes, there's also an application talking about projectile motion, because I tell you that's really, you see this type of thing used a lot in physics, and there's some theta and all that. I'm going to spare you that, this semester, and if you were interested in it, you have nothing better to do on a nice Friday night, you can look through this one and see how we do some of that stuff with particle motion. All right? But that's as far as I'm going to go in this section. Now on your final, just to limit your stress level with this section at least, because I'm not going to test you on this before the final, I'm going to ask you, or I would pay attention to the basic things that we talked about here. Identify the graph of the function, eliminate the parameter, or come up with a set of parametric equations. Okay, those were the three basic topics that we covered. So that's what I'm going to pick from for your final. Right. Otherwise, that's it for that section.